All right, my friends, welcome back. Uh, yesterday, after I did my 30 minutes of primary singing time, I went to nursery to sing with the little kids. My wife happened to be subbing in nursery, so thought it would be fun. There were like two of them there because our ward is on the tail end of a baby boom, but there was this one kid who, as soon as I showed up in the room, he started backing away very slowly into the corner. And I thought how he must identify with all of you, actually, in terms of how you're feeling after the exam. So what I will do, there's still a few people who haven't taken the exam for various emergency reasons, and I will soon enable it so you can go on Learning Suite and see which items you got wrong. If you would like to come to my office and look at the exam together, you're welcome to. Let's see, I won't have your copy of the exam until later today. It usually takes a day to get them back from the testing center. So let's see. Other than that, yeah. So, and we'll talk about how we'll do a post-exam review session a little bit later. All right. We have been talking about chair confirmations, and this summarizes our discussion so far. When the chair flips, you've seen that with the model set, but it involves axial going equatorial, equatorial going axial, up substituents stay up, and down substituents stay down. And we need to just spend a minute on the relative energies of various chair conformations. So I said last time that there's a difference in energy between having the methyl group equatorial versus axial, and that's because of these 1,3 diaxial interactions. We illustrated that in Spartan with an actual space-filling model. It's about 1.7 kilocalories per mole. That's not a number to memorize. I obviously didn't, but that's the accurate number. This difference in free energy between having something equatorial versus axial is one measure of how big things are in terms of OChem. It's a measure of steric hindrance or steric size. And so some organic chemists have tabulated some values for various groups so that you can sort of see what these trends are. These free energy values are sometimes called A values because they come from the axial A versus equatorial conformations in a cyclohexane ring. The squiggly line here represents the rest of the ring to which the OH group is attached, and its A value is about 1 kilocalorie per mole. Just to put things in context, if you remember delta G equals minus RTLNK, at room temperature, a difference of 1.36 or 1.4 kilocalories per mole equals a factor of 10 in equilibrium constant. So you could look at this number and say, okay, there's going to be somewhere less than 10 to 1 equatorial versus axial. If you go to the methyl group, of course, it's a little bit more. Its A value is 1.7 kilocalories per mole, and that means it's going to be more than 10 to 1 in favor of the equatorial versus axial. And I think for reasons that I showed you last time, as you start to add alkyl group, or as you start to add additional alkyl groups to the carbon that's attached to the ring, at first it doesn't do anything to the A value because the additional groups the additional groups we're attaching here can get out of the way. For example, if we come over here to Spartan and we delete some stuff. There, that's an ethyl group on a cyclohexane ring. Here's equatorial. Here's still an equatorial. There's an axial conformation, but do you see how the other group, the methyl group that's attached to the other carbon on the ring, do you see how that swung out of the way? So it's kind of far from the ring. Doesn't make much of a difference. And even when you go, I think I showed you last time, even when you go to isopropyl, that is having two methyl groups attached to that carbon that's attached to the ring, you can still get a conformation where both of those methyl groups are sort of out of the way. And so this gives you something of a sense for how big groups are in organic chemistry. I'll just summarize. The A value for the isopropyl group is 2.6. And then there's going to be a huge jump, as I think I showed you last time, when we go to T-butyl, because now you can't get any of the methyl groups out of the way. Okay, another interest, so one of the things that affects how big things act in organic chemistry is whether or not they can get out of the way of other stuff. Now, there's another interesting and somewhat counterintuitive trend that's worth talking about just a little bit with these rings, with cyclohexane rings, and we'll do the halide series, F, Cl, Br, and I. And you know that I is bigger, and yet, watch the trend in A values. So for fluorine, it's 0.15. That means that there's almost no free energy difference between having fluorine equatorial versus axial. The reason for that, of course, is fluorine is small, and this tells you it's almost the size of hydrogen. We can go look at a space filling model for that. And so there's fluorine in the equatorial conformation. Let's see that space filling. It's a little bit bigger than a hydrogen, but not much. Sometimes people in OChem will say that fluorine is isosteric, meaning it takes up just about the same amount of space as hydrogen. And oh wow, they're actually showing you that the axial conformation is more stable. There is a reason for that, but not one that we will learn. But basically, there's not much. This is much less than a kilocalorie per mole in terms of what the energy. The answer is it's hyperconjugation, but you don't care. And if you want to know more, take my chemistry 552 class. Right? I should stop advertising. There are some of you that are like, don't even try, man. Okay, when we go to chlorine, it's bigger, which we expect, but after we go to bromine, it's not any bigger. In fact, it looks like it's a little bit smaller, and then to iodide, and it's about the same. So the A value stops changing as much as you go chlorine, bromine, and iodide. And the reason for that is that the bonds get longer as the atoms get bigger. You see how that carbon-chlorine bond in the front there is longer than the carbon-fluorine bond. And let's see what consequences that has. So we'll go space filling. If the bond is longer, that means that the sphere is a little bit, for chlorine, is a little bit further out. And so it doesn't bump into the diaxial, the 1,3 diaxial hydrogens very much. Let's see, let's go back to just ball and stick. So yeah, you can see that because that bond is longer, the steric problems with these two other axial hydrogens are smaller. And that's true as well for iodide. Iodide's quite a bit bigger. And yet, because the bond is longer, it doesn't seem to matter as much. So here's the equatorial conformation, and here's the axial conformation. Far enough out there that it doesn't actually make a difference. Go ahead.
Why is the bond longer?
The bond is longer simply because the atom is larger. It literally can't get any closer. Yep. Yes?
Just to confirm, the A, what you're talking about, like the A values?
Yes.
Is the energy that it takes to flip from one conformation to another?
That's the, yeah, and they're uphill because axial is worse than equatorial. Yeah. Yes?
So you said that 1 kilocalorie is roughly 10 times as much in the axial versus in the equatorial versus the axial.
Right. At room temperature, 1.5, 1.4 kilocalories is a factor of 10 in equilibrium constant.
So is that with every 1.4 it's another factor of 10?
That's right. With every 1.4, it's another factor of 10 because equilibrium constant has a logarithmic relationship to free energy. So that would mean that by the time you get here, you're looking at like probably more than 1,000 to 1 equatorial versus axial. Yeah. Yes?
Are the halides also in kilocalories per mole?
Yes, these numbers are also in kilocalories per mole. Sorry.
I just wanted to relate it in my mind.
Nope, that's fine. Yeah, so basically here, the equilibrium constants are pretty close to 1. Of course, if the free energy were 0, it would be 1, but it's pretty close. All right. So the kind of questions that one can ask about this kind of information, and I don't want you to memorize A values. Nobody's asked that yet, but it was probably coming. But I want you to be able to use information. Frankly, you don't need A values to assess how large things are. If you remember the T-butyl group is larger than the methyl group, that's pretty useful. If you remember that the methyl group is a little larger than the hydroxyl group, that's useful. One of the ways to ask questions about your understanding of chair conformations is to draw some cyclohexane ring and then put some substituents on it and ask you what is the best chair conformation or the most stable chair conformation for this molecule. All right, so this, like a lot of questions you get asked, this draws upon multiple skills, okay? Some people will look at that, they will draw a chair, and then they will say, oh look, the most stable conformation should be the one where everything is equatorial. What did I do wrong? You can tell it's wrong because I'm giving it to you as the wrong example. Back in the days of the old missionary guide, this was way before your time. There would always be a more effective example and a less effective example, which in Spanish was menos eficaz. And you'd never want it to be the menos eficaz example. Well, this is the menos eficaz example. This is the bad example. What's wrong there? Yeah?
You have them both as equatorial, but they're not, they have 2 carbons between them, so they're not equivalent. So it goes equatorial, then it goes axial toward axial because you have them 2 apart. It doesn't work. They're both going to be either equatorial or axial, but it doesn't satisfy chair conformations.
So you're saying that based on the distance apart these are, you don't think it's possible for them to both be equatorial, right? Go ahead.
I think they could both be equatorial, but since in your drawing you had them both coming out of the board to us on the same plane, so like they're both, if that makes sense, coming towards us, like you didn't draw a dashed line for one of them. So since they're on the same side, then they both can't be equatorial. One would have to be axial.
Okay. Is that better?
I meant on the first drawing, the one how you have,
Oh.
you have a wedge for both
Okay, there's a wedge for both of, okay, there's the issue of up versus down, coming towards you versus going backwards. These are both wrong. We're going to put the big, what? We lost visual, Captain. Okay, yeah, the problem here is that I didn't bring the adapter thing that turns this on, so we got to just periodically refresh it. I think we got enough battery power for the rest of the class. If we don't, we'll just be done. Because I'd rather be done than use the chalkboard, frankly. Right, so the problem here is that we misapplied the principle. It's true that all other things being equal, having equatorial substituents is more stable, but you got to draw the right molecule first. And what we've drawn here is not the right molecule. So let me show you how that is. We'll just delete that one. Put yourself above the chair, looking down at it. I'm really restraining myself in not drawing Sith eyes today. Here is a 6-membered ring. From our perspective, looking down at that chair, we would have a methyl group here and an OH group here. The OH group would be coming towards our eye, so that would get a wedge. The methyl group would be going away from our eye. That's a dash. Okay, are those two molecules the same thing? No, they are different. They have the same connectivity, they'd have the same molecular formula. They're actually a kind of isomer, but they are not the same. A word for molecules that have the same connectivity, same molecular formula, but are not the same is stereoisomers. Stereo referring to 3D. They're different in shape. We could use a number of different words to describe stereoisomers here. These two happen to be something that's called diastereomers. We'll talk about that a little bit later. And it would be fine to talk about this one as trans. The OH and the CH3 are trans to each other across the ring, and this one is cis. All right, the message is, when drawing chair conformations, first worry about drawing the right molecule, and then worry about which conformation is more stable. So some tools for drawing the right molecule. First, number the atoms of your ring. Second, draw the chair. Then, choose some place to start in the ring, and it doesn't matter where. So we'll start with 1 here. And then if I've numbered counterclockwise here, I must also number counterclockwise here. So I'm going to go 1, 2, 3, 4, 5, and 6. Now I go 1 carbon by 1 carbon, and I ask, okay, carbon 1 has an OH group, and that OH group is up. I have numbered this carbon here, carbon number 1. It is a down carbon, and at a down carbon, an up substituent must be what? Axial or equatorial? Up substituent has to be equatorial. There's no, if there is an axial position there, but that's down. So, OH group is here. Now we keep numbering around the ring, 1, 2, 3, 4. A methyl group on carbon 4, that is up. 1, 2, 3, 4. Carbon 4 here is an up carbon. What's the up position on an up carbon? Axial, okay. Now we've drawn the right molecule. Once you've done that, now it's time to draw the other chair. And there's only ever going to be 2 chairs that are options. So if you're on a multiple choice exam and I say, which of the following is the most stable chair conformation of this molecule, and there's more than 2 options, you should know that I have placed options there that are not the right molecule. Okay, because there's only two, if you get the molecule right, there's only 2 chairs possible. All right, so let's draw the other chair, and I'm going to do this simply by drawing the same basic chair shape, only I'm going to change where carbon 1 versus 2 are. We're going to put carbon 1 at an up position instead of a down position. 1, 2, 3, 4, 5, and 6. 1 OH group should be up. 4 methyl group should be up. Only methyl is equatorial. All right, now and only now that we have drawn the right molecule and drawn 2 possible chairs, now is the only time we worry about which is more stable. So to do this, you can either have an intuitive feel for size. For example, the methyl group has 3 atoms attached to the thing that's attached to the ring, whereas the OH group only has 1 atom attached to the thing that's on the ring. So it ought to be easier for the OH hydrogen to get out of the way than it is for any of the methyl hydrogens to get out of the way. And that's reflected in these A values, where we learn that the penalty for having methyl axial is worse than the penalty for having OH axial. And so I would pick this one as the more stable chair conformation, because it's got less bad, it's got the less bad, or the worst, the not as bad. It's got the biggest thing, equatorial. All right, do you follow that? Yeah, go ahead.
When we're deciding, should we never look at like the size of the atom to decide if that doesn't, moving down, looking at the size, it doesn't really change?
You're talking about here, if I compare these two and the size is the same, or?
Talking more just generally.
Okay.
Like when we have 2 atoms and we're looking at the size of each one, and one's a little bit bigger or something, but that's not necessarily going to help our decision, right?
Yeah, I think your question is, if the atom that's attached to the ring changes in size, what does that do? And that's tricky because size increases, but bond length does too as you go down the halides. So that's a difficult call. I would give you the halide A values, or I can show you an example of that. But I'm really not going to be asking you which is better, to have chloro or bromo axial. Yeah. This series tends to make a little bit more sense. The more things you put on the atom that's attached to the ring, the larger and more problematic it will be to have it be axial. Okay. Let's see. Couple other examples. One of my personal favorites. Now, here we're going to draw a carbohydrate, and I forget which one we're going to draw. I think it's probably glucose. Not sure. Yeah, that's pretty well glucose. Glucose is boring, but okay. So, which of the following is the most stable chair? Well, and you'd have options here. Again, the best thing you can do is to number the atoms of the ring, then draw a chair, and we're going to have to choose a place to put the oxygen. I am just going to put the oxygen there in the front. Now the oxygen occupies a spot in this 6-membered ring that used to be a CH2 group, but we're going to assume for the most part that the chair conformation is the same, that replacing the CH2 group with the oxygen doesn't dramatically change things. So now I'm going to number clockwise, looks like, around the ring, making sure I follow the same pattern. And then all I have to do is go carbon by carbon and make sure that the substituents are in the right place, meaning down versus up. So on carbon 2, I have an OH group that is down, which here must be axial or equatorial. Equatorial down, and I'm going to draw it parallel. The front carbon and 2 and the back carbon 5 are often difficult to deal with because you have to really have a sense for perspective. If you get lost, just remember that the equatorial substituents on either of these carbons need to be parallel to these bonds on the edge. So OH is here. Carbon 3, OH is down. So on this carbon, where is the down position? It's axial, good. Carbon 4, the OH group is up, so that would be up axial. Carbon 5, the OH group is down. So I'm going to have to move my number 5 somewhere. That did not work. Oops. That's because I keep pressing undo. Okay. So we're going to draw the line straight down, and we have to, in some cases, just sort of imagine because it's difficult to draw a 3D model. So what I'm intending to communicate, we got to move the 2 as well, sorry. What I'm intending to communicate is that we have an OH group that's axial down on that carbon in the back, and then carbon 6 has a CH2OH attached to it. So, and that's up, and at carbon 6, the up position is axial. So now I can check and make sure I've gone around and I've got everything in the right place. Yeah?
We just know whether it's supposed to be down or up based on how it's drawn, whether it's coming towards us or away from us?
Yes, we just know whether it's supposed to be down or up because it's drawn here up for, towards us or away from us. Yeah. Yes?
And that can be axial or equatorial.
Down, yeah, down can be axial or equatorial, up can be axial or equatorial, which will depend on where you started when you drew your ring. But remember, we're not going to worry about whether we got the right answer when we first draw our ring because there's only ever 2 chairs and we're going to draw them both. So if you're looking at this and thinking, goodness, look at all the stuff that's axial there, isn't that bad? We don't care yet. We just care that we got the right up-down relationships. Okay? Yes?
Is it arbitrary which ones you label up and down to begin with?
Is it arbitrary which one you label up or down to begin with? Yes. I just chose, in fact, I deliberately chose to put the oxygen on the down position because I knew this would draw the worst chair first. And I wanted to show you that I didn't care that we drew the worst chair first. Yeah. Uh-huh.
With the numbering 1 to 6, like, do you care where you start with 1, or is it?
Do you matter where you start with 1 when numbering 1 to 6? No, not at all, as long as you're consistent. Yep, and as long as you go around in the same direction. Right? So now I'm going to draw the other chair, and I need to put oxygen not at an up. I need to put oxygen not at a down carbon position, but an up position. So we could do that, and that would be fine. Alternatively, if you wanted, we could do this, and that would be fine. If you want to get even crazier, we could do like this, and that would be fine. So whatever. Now let's go around again, numbering in the same sense. Looks like clockwise. 1, 2, 3, 4, 5, 6. And now we'll continue to go around the ring, putting things in the proper up-down orientation. Carbon 2 has a down OH group. At carbon 2, the only down position is axial. Carbon 3 has a down OH group. At carbon 3, the down position is equatorial. Carbon 4 has an up OH group. At carbon 4 in this chair, the only up position is the equatorial one. carbon 5 has a down OH group, and at carbon 5, as we've got it in this chair, the down position is equatorial. Carbon 6 has an up CH2OH group, and at carbon 6, the only up position available is the equatorial one. Okay? And if we've actually drawn the chairs correctly, everything over here, there should be a switch from axial to equatorial and vice versa. So notice how every time you go around the ring, whatever used to be equatorial should now be axial. All right? So now we've drawn the two chairs, we've compared them, we know that they're the same molecule, just different shapes. So which one is stabler or more stable? I'm getting, yes, okay, right. Ah, yes, okay. You guys are pointing this way, and I'm like, no, it's not the one on the left. Yes, this is the better chair.
So does the fact that we have a hydroxy group next to our CH2H cause issues too?
So you're looking here and seeing that these two are gauche to each other if you look down the bond. And that might not be the best possibility. I mean, here they're anti to each other, but there's other gauche things that would happen. For example, being axial makes you gauche to the ring and gets you these 1,3 diaxial interactions too. So this is as good as we can get. Yeah?
Sorry, how did you know that that was the most stable? It was pretty clear when we only had one group that we were looking at, but with multiple groups, how can you tell?
Right, so how can I tell with multiple groups? Well, here I'm going to count the number of the things that are axial. I've got 1, 2, 3 axial OH groups and 1 axial hydroxy methyl group, CH2OH. Over here, I just have 1 axial OH group and everything's equatorial. Yep. Uh-huh.
So say you had like 3 axial OH groups and then 1 equatorial with CH2OH.
Yeah.
Would that like override the other?
Yeah, so I think you're proposing a situation maybe like this where and the answer is, I don't know. I mean, you would just do the experiment and see. I think you can, to some extent, treat A values additively. So my gut response is that, yeah, 4 axial OH groups probably do overwhelm the CH2OH, but in the examples I will give you, it will be a pretty clear choice. Yeah. That is a carbohydrate. I don't know which one it is. And had this been a question on a multiple choice exam, you would have seen a lot of other options, many of which would have been stereoisomers, but not the right molecule. And I could have gone on and on like all day with other options. So if you haven't learned, don't count on solving my exam problems on process of elimination, because there's going to be like A through J. But if you know your stuff, it's actually really straightforward. You draw the two chairs, and then you find those chairs and the answers, and then you choose which one is the right one. Okay. So I think that's probably enough on A values. Now, I want to go back to this issue of stereoisomers, which is really, really important in OChem. So it's actually decent that we're talking about chairs. I'm going to draw 2 different carbohydrates that have dramatically different fates when you ingest them. So you've got cellulose, component of plant cell walls, and it is an extended polymer of carbohydrate molecules linked to each other in the following way. And then I'm going to put each of these individual carbohydrate units is glucose, and they are linked together with this sort of shape. Now I'm going to draw for you starch. In particular, the carbohydrate I'm drawing for you is called amylose. And it's going to have the same basic subunit except for one thing. Getting sick of this. Okay, let me answer the question that I know someone is worried about. Do we have to memorize the structure? No. You don't. Okay, look at those two. And I didn't, I should have just drawn, I thought I'd drawn 3 over here. Fine, we'll just get rid of that and do our little squiggly line. This is a repeating subunit. Squiggle. Now, there's a difference in shape between these two. Can you see it? This one, yes. This one's sort of laid out straight. This one has a more of a step down kind of shape. It all comes down to whether or not a group is up versus down at what we will call carbon 1. Over on the left in cellulose, the oxygen on carbon 1 is always up. Oops. Whereas in amylose, carbon 1 is always down. Now that has a big effect. You can suck on a saltine cracker and your saliva, I don't know why you'd want to, but your saliva has enzymes that can break this bond, and it will start to break the starch down into glucose, and actually if you swish that disgusting mess around in your mouth for long enough, it'll start to taste sweet. You can swish celery around in your mouth for as long as you want, and nothing's going to happen to the cellulose, at least not until bacteria get a hold of it. And you don't have enzymes to break this bond. Okay, your enzymes pay attention to shape, and so shape of molecules, because of whether or not groups are up versus down, can be really important. Again, we're going to call these two molecules, same connectivity, just different shape. They are stereoisomers. And in this case, they are diastereomers. And I'll explain that term in a little bit, which little bit is now, unless you've got any questions about cellulose versus amylose. Yeah?
Just confirming quickly, you said stereoisomers have the same connectivity, just a different shape.
Same connectivity, just different shape. And that will usually be because of something that's up versus down. Yeah?
So this doesn't, just because we have enzymes that break down the starch, doesn't necessarily mean that the other bonds in the cellulose are stronger, it's just that it's a different enzyme.
That's right. It is the same, it is basically favorable for these bonds that I've highlighted to break, but you need a catalyst to make it happen at an appreciable rate, and you don't have the catalyst for the cellulose, whereas you do here. Yep. All right. So, in the world of stereoisomers, there are only two kinds. There are two kinds of stereoisomers, and Actually, I'm afraid that you're going to apply what I'm drawing to cellulose and starch, which is not my intention. So, stereoisomers come in two different flavors and only two. One is diastereomers, and the other is something called enantiomers. And enantiomers are mirror images. Molecules that are mirror images of each other are enantiomers, but they are not the same. Diastereomers are all other kinds of stereoisomers. So, examples of diastereomers that you have already encountered: alkenes, cis versus trans, or E versus Z. That is a diastereomer issue. What we saw just a few minutes ago with cis versus trans about a six-membered ring is a diastereomer issue. And there will be other kinds of diastereomers too. Enantiomers, though, it's a very specific thing. They have to be mirror images, but they are not the same thing. So this is where you need to develop some new spatial reasoning skills. And this is where actually your day-to-day experience may help you. Your hands are basically mirror images of each other, right? What's on your left and my right is a reflection of what's on my left and your right, whatever. Get that wrong. Do you know I get my right and left wrong, exactly wrong most of the time? If I have to choose really quickly, oh yeah, my right hand. No, that's not it. I think it's genetic because my grandma jokes that she has to tell my grandpa, throw a rock, Dale, throw a rock. That's your right hand. Okay, all right. Anyway, they are mirror images of each other, but if you want to stick your right hand up inside of your left hand, you can't line up everything. And you can sit there forever, worlds without end, trying to do it, and it will not happen. Okay? They are mirror images of each other, but they're not the same. You've also encountered this when you've looked at yourself in the mirror and then seen a picture of yourself and wondered, whoa, what happened? That's because you're seeing your mirror image and everybody else is seeing what you actually look like. And they're not the same. And the ability to have a mirror image that is not the same is a property that is called chirality. Chirality is a word we use to indicate that something has a mirror image that's not the same. By the way, diastereomers, they may be chiral or they may not. But all enantiomers are chiral. So we'll just write that here. All enantiomers, or actually a better way to say this is all chiral molecules have an enantiomer. Okay, so I'm going to show you how this works and how you recognize enantiomers, and we're going to be drawing this on just flat paper, though you may need some models to help you out with this. So let me draw an example of molecules that are chiral versus not chiral. Oops. That's fine. Here is a mirror Ooh, now I get to use, did you guys know Notability had an update? Now I can draw dotted, come on, draw dotted lines like that. Whoa. Just blew my mind. Okay. I'm going to draw the mirror image. This is the mirror. And so mirror reflection operations are a sort of back to front thing. What was close to the mirror on this side is close to the mirror on the reverse side. So I'd put a CL here and a CL there. Right and left stays the same. Oops. Except I'm not drawing very well, so sorry. Now, are those two, they are mirror images of each other. Are they the same thing?